So this week we're going to start learning how to graph trig functions, and we're going to start with the sine function. So when I'm talking about the sine function, I'm talking about y is equal to the sine of theta. Now when we talk about graphing, usually we use the equation in terms of y and x, so you can also write it as y is equal to the sine of x, but you have to remember that because x is inside a sine, so you're taking the sine of x, x is really an angle measure. Now, when we graph the sine function and we graph other trig functions, we want to always use the measure of theta in radians. So remember, you're measuring the angle theta, and you want to always use it in radians. Another thing that you want to remember is that the sine of theta is equal to the y value of the point of intersection between the unit circle and the terminal side of the angle of theta. So we're just going to jot that down and remind ourselves what the sine of theta actually is. So remember, the sine of the angle theta is the y value of the point of intersection where the unit circle intersects the terminal side of the angle theta. So we want to keep that definition of the sine of theta or the sine of x in mind, that we're really just talking about the y value of the point of intersection. So let's remind ourselves what those points are using our unit circle. So when we talk about a unit circle, the unit circle always has a radius of 1. So if this circle, this unit circle, has a radius of 1, then that would make this point 1, 0. This point would be 0, 1. This point would be negative 1, 0. And this point would be 0, negative 1. So what I want to do is I want to label all of my points as with the radian angle measure. So for example, if I have my initial side here and my terminal side ends here, that is an angle measure of 0 degrees, or in radians, we would say 0 radians. Then if I go up 30 degrees, 30 degrees is the same thing as pi over 6 radians. 45 degrees is pi over 4 radians. 60 degrees is pi over 3 radians. 90 degrees is pi over 2. So then a full circle, if you remember, a full circle, 360 degrees was the same thing as 2 pi. And then half of the circle then would be 1 pi, or just pi. So a quarter of the circle is half of pi, or pi over 2. Why don't you go ahead and fill in the rest of the radians? Press pause on the video, fill in the rest of the radians from your unit circle work from last week, and then press play when you're ready to continue. So as you can see, I just filled in the rest of my angle measures in radians. Now we need to fill in our unit circle because we need all these points of intersection. So remember, this is the initial side of the angle. The terminal side would be here to get a measure of pi over 6 radians for our angle measure. Where this terminal side intersects the unit circle, that's our point of intersection. And those are the points that we need in order to know our x and our y values, our sine and our cosine values of the angle. So at pi over 6, and this is just continuing the work from last week, we have a point of intersection at root 3 over 2 and 1/2. At pi over 4, our point of intersection is root 2 over 2, root 2 over 2. And at pi over 3, we have 1/2 and root 3 over 2. So why don't you press pause, fill in the rest of the points of intersection, and then press play when you're ready to move on. As you can see, I just finished filling in my points of intersection on our unit circle, so we know all of our x and our y values. So I just want to do a little reminder that the cosine of angle theta is equal to the x value of those points, and the sine, the sine of angle theta is equal to the y value of those points. So that means that the sine of theta is equal to the y value of those points. So what we care about right now are all of these y values at each of these points. So when I graph the sine of x, y equals the sine of x, or y equals the sine of theta, we're focused on all of these y values at these points of intersection. So that's what we want to keep in mind right now. So as you can see on my graph here, I've already labeled our x-axis, and our x-axis goes from 0 to 2 pi. So we're talking about doing a full 360 degree or 2 pi angle rotation all the way around the circle. So we're going all the way around the circle. We are also, so since we're counting from 0 to 2 pi, halfway between would be pi. Halfway between 0 and pi is pi over 2. Halfway between pi and 2 pi are 3 pi over 2. So then for our y values, what is the highest y value that we're going to need for this graph? So the highest y value is 1, because what is the maximum height that this rotation is going to have? So if you think back to our Ferris wheel problem and how we started with our little car on our Ferris wheel, and then we move the Ferris wheel counterclockwise, the highest we could go on that Ferris wheel is the radius of the circle. Well, what's the highest height we're going to have on this circle then is 1. So I'm going to count by halves on my y-axis, and I'm going to have 1, 2, -1, -2. We could have counted by quarters if we wanted to. For the sake of this graph, we're just going to count by halves. So at 0 radians, what is our height here? How high would our Ferris wheel be? Our Ferris wheel would be 0 feet off the ground, right? So we would have a y value of 0. Well, what's the sine? Remember, we're graphing y is equal to the sine of x, or the sine of theta. What is the sine of 0 radians? It's this y value. So y is equal to the sine of 0 radians. I meant to plug in 0, not theta again. That means that, according to this, y is equal to the sine of 0, y is equal to 0. And that matches what we understand about like the height and the co-height of each of these points that we've talked about before. So at 0 radians, we're at 0, a distance of 0 on our y-axis. At pi over 2 radians, the sine of pi over 2 is equal to 1. So at pi over 2, we're at 1. At pi radians, so over here, our y value is 0. We're at a height of 0. At 3 pi over 2 radians, our y value is -1. So the sine of 3 pi over 2 is -1. And at 2 pi radians, we're back here. Our y value is 0, so we're back at 0. Now, what if I wanted to fill in some points in between there? Well, we would have, if this is 0 and this is pi, we have 1, 2, 3, 4, 5, 6. That means that we can count by sixths. So this would be pi over 6. This would be 2 pi over 6. This would be 3 pi over 6, 4 pi over 6, 5 pi over 6, and then pi. So 2 pi over 6 reduces to pi over 3. 3 over 6 reduces to 1 over 2, so pi over 2. 4 over 6 reduces to 2/3, so this is 2/3 pi, or 2 pi over 3. What are our y values at those pi? Those radian values, sorry. So pi over 6, our y value is 1/2. Pi over 3, our y value is root 3 over 2. What does that mean in terms of our graph? Let's take the square root of 3 and divide it by 2. And we're at 0.866, so somewhere up here. And then 5 pi over 6, we're back at 1/2. Oh, I skipped pi over. Actually, I just grabbed that at the wrong value, but it should match 2 pi over 3 anyway, so we're fine. And so we're starting to see a good picture of what our curve is doing. What our sine curve is doing here. And this should remind you of the Ferris wheel problem we did a couple weeks ago. Then again here, we're going to have pi to 2 pi. We have 6 spaces in between, so we're counting by sixths. So if this was 5 pi over 6, this would be 6 pi over 6, which reduces to just pi, which we already have. So then this would be 7 pi over 6. This would be 8 pi over 6. 9 pi over 6, which is 3 pi over 2. 10 pi over 6, 11 pi over 6, and then 2 pi. Or 12 pi over 6, which reduces to 2 pi. And I need to reduce, see, 11 pi over 6 is fine. I need to reduce 10 pi over 6, which should reduce to 5 pi over 3. And then reducing 8 pi over 6, we're going to have 4 pi over 3. One of the things I miss the most is you guys being in class and like catching my mistakes for me. Okay, so at 7 pi over 6, we're at negative 1/2. At 11 pi over 6, we're at negative 1/2. And then at 4/3 pi, we're at negative root 3 over 2, so that should be like negative 8.66. And then same for 5 pi over 3. And we see our curve do this. So what we have here is we have y equals the sine of x. This is a periodic function. And this is a periodic function because this pattern or this cycle is going to repeat over and over and over again. Because we did one full rotation of 2 pi, and then if we go around the Ferris wheel again, we're maintaining that same height. So that height is never going to change at each of those angles. So we know that we have a periodic function. So y equals the sine of x is a periodic function. We also know then that we have a period and we have an amplitude. So it takes between 0 and 2 pi to have one full cycle of y equals the sine of x. So the period of this function then is 2 pi. The amplitude is, remember, the vertical distance between the midline. So our midline is the x-axis here, y equals 0. And the amplitude is the distance from that midline to the maximum, and the midline to the minimum. This distance is 1. This distance is also 1. So our amplitude is 1. And we have a period of 2 pi. So this example in our notes is just focused on being able to read the graph y equals the sine of x and finding the sine of an angle measure based on the graph. So if I want to find the sine of 2, where am I going to look for the sine of 2? Well, pi, we know, rounded, is 3.141. Pi divided by 2 then is 1.57. And it looks like we have 10 spaces here. So like this would be 1 pi over 10, this would be 2 pi over 10, etc. 3 pi, 4 pi, 5 pi over 10 reduces to pi over 2. Pi over 2 is the same thing as 1.571. And we're trying to figure out what the sine of 2 is. So I need to get closer to 2 as a value here. So then this would be 5 pi over 2. This would be 5 pi over 10, 6 pi over 10, 7 pi over 10, 8 pi over 10, and 9 pi over 10. So I need to figure out where 2 is between 1.571 and 3.141. So 6 pi divided by 10 is 1.88, so we're getting closer. 7 pi divided by 10 is 2.1. So 2 is between 6 pi over 10 and 7 pi over 10. So I'm just going to estimate that 2 would be like right here. We'll call this 2. So what is the sine of 2? The sine of 2 is equal to whatever this y value is. Did I do that correctly? Yeah. So that y value is going to be between 0.5 and 1. So how many spaces do we have here? 1, 2, 3, 4. This was divided by 8ths. So this would be 4/8. This would be 5/8, 6/8, and 7/8. So it looks like we are slightly above 7/8. So 7 divided by 8 is 0.87. So I'm going to just estimate that this y value right here is probably 0.88. So the sine of 2 is equal to 0.88. And we can actually plug this into our calculator and see how close we were. So what's the sine of 2? And my calculator is incorrect because my calculator is in degrees, not radians. So we actually have to change our calculators to do their measure in radians. So I'm just going to go to mode and I'm going to select radians. Because when I plugged in the sine of 2, my calculator was automatically in degrees, and the sine of 2 degrees is 0.03, which is not anywhere close to what we have here. So when I plug in the sine of 2 radians into my calculator, I get 0.90. So our estimate of 0.88 is actually pretty good. I'm not mad at that at all. I would accept that as an answer because we are estimating the values of sine using our graph. So why don't you go ahead and figure out the sine of pi, the sine of 3, the sine of 3 pi over 2 using your graph, and then press pause, press play when you're ready to check your work. So the sine of pi occurs at this point here with a y value of 0. The sine of 3 pi over 2 occurs at this point here with -1. And then the sine of 3. So if 3.141 happens here, I'm going to assume 3 occurs around here. And we'll say that's a y value of, remember we were counting by eighths here, so that would be 1/8 about. So 1/8 is 0. Definitely not 0.25. What's 1/8? 0.125. There we go. And let's just see if my calculator agrees with me. So the sine of 3 is equal to 0.141. Yeah, 0.141, close enough. So that's how I'm going to know whether or not you're actually using the graph to estimate these values, or if you are using your calculator. Because we're using our graph, we're going to be off just a little bit by a couple hundredths, and I'm okay with being off by a couple hundredths. Because we're doing an estimate, it's not going to be that exact value, which we're okay with. All right. Good work today.